All right, so I'm doing another video just because it was easy enough last time, finishing some of the examples that we didn't do in class. So number 9, we had started but not finished, so I'll keep working on that one. So here we had the limit of this function here as x goes to 0, and we rewrote it as e to the log of that whole function in order to bring that 1 over x out in front and then just deal with an indeterminate product. So if we do just let x go to 0 here, we can see that 1 over x would go to plus or minus infinity, and then this log part would go to minus infinity, no, 0. Anyways, so we have infinity times 0, which is indeterminate, so we can deal with that now. So let's look at this. So we've got the limit as x goes to 0. Well, this 1 over x we could just put as our denominator, just x. And then on top we've got log of, well, what I'll do here, and this is something I'd started to do in class, but I was, whatever, all over the place. Not a good day. Anyways, what we're going to do is we're going to use the log law that tells us that the log of something a divided by b, let's say, is log of a minus log of b. And so instead of having log of that numerator over 3, we can have log of a to the x plus b to the x plus c to the x minus log of 3. Okay, well now what we've got, if we just plug in x is equal to 0, we'll have 0 in the denominator, and then on the top we'd have log of 3 minus log of 3, and so 0. 0 over 0 means we can use L'Hopital. All right, so if we take, using L'Hopital, let's recall, means just taking the derivative of the top and the bottom. Derivative of the top, well, derivative of log of anything is 1 over that thing. And then by the chain rule, derivative of the inside. And here, these are exponents. So, but with weird bases. Well, not weird, it's just that they're not e. So we get log of a times a to the x plus log of b times b to the x plus log of c, natural log of c times c to the x. Then, the natural log of 3, by the way, that's a constant. So that derivative of that is just 0, so we lose that. And then the denominator, we've got 1. And we can check again to see if we've got an indeterminate form, and we do not anymore. If we actually just plug in x is equal to 0, we see that we get 1 over, well, a to the 0 plus b to the 0 plus c to the 0. That's just going to be 1 over 3. And then in here we get log of a plus log of b plus log of c. So we can call this 1/3. Then, using the log law, log of, I don't know, we use the sum of logs becomes a product. So here, log of a plus log of b plus log of c becomes log of a times b times c. And this 1/3 in front, we can actually turn into a cube root. So we can think of this then as log of cube root of ABC. Therefore, if we go back to the actual limit you were trying to solve, the limit as x goes to 0 of e to the 1 over x log of a to the x plus b to the x plus c to the x over 3 is equal to e to the log cube root ABC. And so cube root ABC. Isn't that great? Everything simplifies quite nicely. I bet you could show that just kind of looking at this, I wonder, I don't know, for, I guess, unofficial bonus points, I'm going to guess that the limit is x goes to 0 of, let's say, a1x plus a2x all the way up to anx over n to the power of 1 over n, or x. I'm guessing that this, so instead of just having 3 letters, we have n of them. I'm guessing this is going to end up being the nth root of the product. I don't know. If you want something fun to do, try that out. Okay, so then we did skip a question earlier. What I'm going to do is go through numbers 10 and 11 and then go back up to the one that we had skipped. Okay, so number 10, we've got another one where we've got an exponent. So let's see what happens if we plug in x is equal to 0 first, and what that means, I don't know, if we even have to do a bunch of rewriting. So as x goes to 0, the base, 1 minus cos 2x, this goes to 0. And then as x goes to 0 from the right-hand side, 1 over log x will go to, well, 1 over negative infinity. And so that gives us 0. So here we've got a 0 to the power of 0 type. Okay, so that means we've got to use our exponent and log trick. It's not a trick, it's just that they're inverses of each other, but it's a technique, right? So we've got the limit as x goes to 0 of e to the log of 1 minus cos 2x to the power of 1 divided by log x. And as before, we bring out that 1 over log x. We need an e as well. So we have e to the 1 over log x, and then log of 1 minus cos 2x. Okay, well, now, as before, we'll look at what this limit is, and then just take e to that power. So the limit as x goes to 0 of, well, here let's again just take the fact that we've got this 1 over log x and put that as our denominator. And in the top, we can just leave the 1, or the log of 1 minus cos 2x. Okay. Now, as x goes to 0 from the right-hand side here, we would get negative infinity over negative infinity, which is indeterminate, and we can use L'Hopital. Let's see, so using L'Hopital, derivative of log of 1 minus cos 2x is 1 over 1 minus cos 2x times the derivative of the inside, so that's sine 2x, and then times 2. And then on the bottom, we have 1 over x. Now, for a lot of these, you'll notice that we end up kind of rearranging things just to look a little nicer before we consider applying L'Hopital again. Because if you end up having to do that, may as well make your derivative not as messy, you know? Okay, so what we're going to do here, actually, I'll give us some space. Just to clear this denominator of 1 minus cos 2x, we're going to multiply everything by that. That's usually a technique that works pretty well, is clearing denominators. And so if you kind of just train yourself to be like, oh, that's so annoying that we have all of these fractions, then, that's a good, I don't know, good intuition. Let's also multiply by x, because we also have that 1 over x. So multiplying everything by 1 minus cos 2x and x, on the top we're left with 2x times sine 2x. And in the denominator, you've got 1 minus cos 2x. And that's it, actually. Don't even need that bracket. Cool, okay. Well, if we do just put in x is equal to 0, we see that we'd get 0 times 0 on top, 1 minus 1, so 0 on the bottom. 0 over 0, indeterminate. You can use L'Hopital again. So let's do that. Here we can use the product rule. So we have 2 sine 2x plus 2x times cos 2x times 2 over derivative of the bottom, which is 2 times sine 2x. And as before, we can simplify a little bit. Well, okay, what I'm going to do to start off with is just kind of get rid of a 2 from each of these factors. Then split this up into 2 fractions. So we've got limit as x goes to 0 of sine 2x over sine 2x plus 2x, and then it's cos 2x over sine 2x. Cool. Well, this first term is just 1. Or I'll keep it all in the limit, why not? So you have the limit as x goes to 0 of 1 plus 2x cos 2x over sine 2x. But this 2x over sine 2x, we know will give us 1 as we take the limit. And then we've got cos 2x, which is also going to be 1. And so then together, this limit is just 1 plus 1, so 2. Cool, right? And then the final answer then, if we go back to the original question, because again, we were working in the exponent. So the limit as x goes to 0 of e to the 1 over log x, ln 1 minus cos 2x. This gives us e squared. Wonderful. Okay, now for number 11, we've got the limit as x goes to infinity of x plus sine x over x plus 1. Okay, well, I guess just looking at this one, it's kind of interesting because it's like we've got x plus something that's bounded, or I'll write the full word, bounded, above by 1, over x plus just 1. So we're going to just make a guess that this limit is equal to 1. Now, of course, we're going to actually work it out, but, in theory, like, okay, if on the final exam you had a limit that looked like this and you were running out of time and you wanted to, it was multiple choice, this would be a decent way to choose that, but we'll see what it actually is. Okay, so as x goes to infinity, we have infinity over infinity, so we can use L'Hopital's rule. So by L'Hopital, this is the limit as x goes to infinity of 1 plus cos x. Oh, wait. We might not need to do that, actually. Yeah. Okay, well, if we do that, let's see. We get cos x. Cos x does not converge as x goes to infinity, and so then we just kind of have something weird. So actually, I'll show what we'll do instead for this one. go back to the original question, and that initial like intuition, what we can do is we can take out what's growing fastest in each of the top and the bottom. So here we're factoring out what's growing the fastest. So here on the top, taking out an x, we have 1 plus sine x over x. And on the bottom, we have 1 plus 1 over x. Okay, well, these x's will cancel out. So we can just, I don't know, the easiest way to write cancel out. And then what we're left with is not so bad. So here we have just 1 plus sine x over x. And we already know sine x over x goes to 0 by the squeeze theorem. And you can double check that if you'd like. And then this also goes to 0, so we just get 1. So I guess this is a good example of one where trying to just use L'Hopital actually doesn't really help us because we get something that isn't necessarily defined. So that's kind of interesting. Now let's, I guess, go back to the one we skipped. I guess the nice thing about a video is that you can pause it if you need to. Okay, there's number 3 here. But I don't expect that we'll need this full page. Okay, so we're looking at the limit as x goes to 0 of sinh x minus x over x cubed. Now, if it helps, remember sinh x is equal to e to the x minus e to the negative x over 2. And so if we let x go to 0, we can see clearly here that sinh of 0 is equal to 0. So as x goes to 0, then here we get 0 over 0. I'm just going to take out the answer for now, then, which is indeterminate. And that gives us then an occasion to use L'Hopital. So the limit as x goes to 0 of, so here we had sinh, derivative of sinh is cosh. So we now have cosh x minus 1 over 3x squared. Well, here we get 1 minus 1 over 0, so 0 over 0, and we can use L'Hopital again. Derivative of cosh is sinh. That is one way that the exponential functions differ, or the hyperbolic functions differ from the trigonometric functions we're familiar with. Is like a lot of those derivatives are the same, but some of them are different. So here, sine and sinh and cosh, you never get those negative signs when you're taking the derivatives. Right, so then here we've got sinh over 6x. This is again 0 over 0. So let's take L'Hopital, or take the derivative again by applying L'Hopital's rule. And in the numerator, we'll now have cosh x, and then in the denominator, we just have 6. And now this is just going to be cosh of 0 over 6, which is 1 over 6. So that's it. Thank you for watching. I'm going to just kind of scroll down to the textbook questions and see if there are any, just looking at them, that I would for sure suggest doing. Oh, okay. So yeah, 7 to 66. That's a lot of limits. If you do all of those, you're going to be like so good at limits. But especially if you, because the thing is, it's not just about doing a lot of practice problems, it's about understanding why you use the method for each. So, you know, if you do all of these, but you haven't like internalized some kind of a, I don't know, like flow chart or something of like when to use each technique, then you won't know what to do with like a weird limit on an exam. But this is a really good list of limits. And as always, if you don't know how they get to the answer that's given at the back of the note package for any of these, for the odd ones, or if you want help with some of the even ones, you can always come to me. Some of these I might specifically point out as ones to do over reading week when I put together that list of problems. Let's see, all the other questions are good, but I would say less essential probably. Although some of these are kind of cool. Let's see. I don't know. 85 and 86 are kind of cool. I'm sure some of these application ones are cool as well, but I'm more of a pure math girly. Anyways, so I'm glad that we were able to work through the rest of these. Hope this was helpful. Bye. See you Friday.